A soft drink bottling company is using data to make sure that the machines used to fill the bottles are doing so properly. A random sample of 50 20-ounce bottles are selected and checked. The average fill for the sample was 19.91 ounces with a standard deviation of 0.1 ounces. Find the 95% confidence interval for the actual fill. The problem is essentially that a company that is filling bottles that say that they have 20 ounces on the side needs to make sure that they're filling the bottles to the proper fill weight. They hope that the population mean for the fill weight is 20 ounces. Now, they don't expect for any one bottle that they could possibly pull off of their production line to contain exactly 20 ounces. But they do expect that the population mean is 20 ounces or not significantly different from 20 ounces. Now, when they take the sample of 50 bottles and they find a sample mean, that sample mean could be a little bit to the right of 20 ounces, assuming that this is the actual population distribution. It could be a little bit to the left. It could be a lot to the left, or it could be a lot to the right. But the problem is that that sample mean, X bar, which in this case was 19.91, we have to remember that it is only a sample of 50 bottles. It's not all of the bottles that go through this process. So just to say that the mean is 19.91 ounces really isn't sufficient. What would be sufficient, though, would be to define an interval with a left end point and a right end point, where we would take this mean and subtract some quantity from it, and then add some quantity to it and say, well, we feel that the actual population mean is between these two values. And if we subtract enough and add enough, then most of the time it's going to be true that the population mean will be between those two values. If I were to take roughly the same interval here and subtract it and add it, I can see that here, if the sample mean is here, the population mean would be in between there. Even if I'm way out here, if I subtract enough and add enough, I'm going to get a sample mean so that when I subtract and add this amount, the population mean is going to be in there. Sometimes it's only going to barely be inside that interval. But sometimes, and only when my sample mean lands way up in the tail or way down in the left tail of the sampling distribution, that width that I subtract and add would not be sufficient to contain the population mean. But this is only going to happen very rarely, only when I'm way down in the tail to the left or way up here in the tail to the right with the sample mean. Now, this can all be summarized using the normal distribution, since from the central limit theorem we know that if n is at least 30, the sampling distribution is normal. If the sample size is at least 30, the sampling distribution is normal. That's the central limit theorem. So, if I were to get out the normal table and start looking at the probabilities that X bar would land up in these tails in certain places, I'd find that if Z is equal to 1.96, then out here in these tails of this curve, we would have 0.025 up in one tail and 0.025 down in the left tail. In other words, if I've got a normal curve, and I'll find some space to draw one here. If I've got a normal curve, the population mean here, with a Z equal to 1.96, and then a Z equal to minus 1.96, I'd have 0.025 of the area out in the left tail and 0.025 up here in the right tail. Now if I define the width of this interval using this z equal to minus 1.96 and 1.96, then I can construct an interval so that only 5% of the time, only when I land way down in the bottom or way up in the top, adding those together I'd get 0.05 or 5%, only 5% of the time would I wind up with an interval that doesn't contain the population mean. So there's a formula for doing that, and it looks like this. The interval would be x bar plus or minus z times sigma over the square root of n. This would be two interval endpoints. It would be x bar minus z times sigma over the square root of n, and x bar plus z times sigma over the square root of n. If we were to go back to this problem and identify all the pieces, we'd find that the sample mean x bar is 19.91. The sample standard deviation was 0.1. The size of the sample was 50. If I'm supposed to find a 95% confidence interval, then looking this up in the normal distribution table, I can see that z would be 1.96. So what we need to do here then is plug these numbers into this formula, 19.91 plus or minus 1.96 times sigma 0.1. Now we're using S as an estimate for sigma. Since we don't have the population standard deviation available to us, we're using S, and we can do that as long as n is at least 30. So whenever n is at least 30, S is a reliable estimate for sigma. Now we could go through the process of using a calculator to find this, and we'd find our interval endpoints. We can also go to www.volstate.edu/jmore/calculators/calculators.htm, and then click on large sample z interval, and then plug these numbers into the boxes here. The sample mean is 19.91. Standard deviation is 0.1. It says if the population standard deviation is unknown, the sample standard deviation can be used in its place when the sample size is at least 30. It's 50. So we can use the sample standard deviation here. The z value would be 1.96. We'd look that up in the table. Alpha is 0.05 when we have a 95% confidence interval. Alpha is the area out in the tails that we were talking about here, which is 0.05 when z is minus 1.96 and positive 1.96. We hit calculate, and it gives us an estimate here of 19.88. We would use the same rounding as the estimation or the estimate of the mean here in the sample mean, rounded to hundredths. We would be consistent with that rounding when we do our interval endpoints. So 19.88 to 19.94. Now the interpretation of this is important. What we looked at was that if we use z equal to 1.96, then 95% of the time that we make these intervals by subtracting some and adding some from the sample mean, then the population mean would be contained inside that interval. There's the sample mean, there's the population mean, and it's contained inside the interval unless the sample mean lands way out here in the tail past where z is equal to 1.96. There's the population mean not in that interval this time. So since 95% of the time the population mean would land inside of an interval constructed using this method, then we can interpret the interval by saying with 95% confidence the population mean lies between 19.88 and 19.94 ounces in this case. Another way to say that would be go more along with the application would be to say we are 95% confident that the actual fill weight is between 19.88 and 19.94 ounces. Now, something that we might want to notice is that 20 ounces is not inside this interval. We're supposed to be making a determination as to whether or not we're filling these bottles to what we say we're filling them to. Well, if the sample or if the population mean we're saying with 95% confidence is between 19.88 ounces and 19.94 ounces, then we are not filling our bottles to the proper amount, and we should probably adjust the machines to fix that.